Okay, so in the last class we have discussed about the electrical conductivity of metals, and it explained using the free electron Fermi gas model. So conductivity is explained, and resistivity is another important term which is connected with the conductivity. So now we will discuss the resistivity of metals. So you know what is the resistivity means, or resistance to the flow of electron or conduction in a metal system. So it is the opposition to the flow of electrons in a conductor or metal system. So how does this resistance arises? The resistance in the metal system arises mainly because of the collisions of these electrons, these moving electrons, with the with other electrons, or with the phonons or impurities present in the system. So these collisions can be classified into two types: collisions with the lattice phonons and collisions with impurities and imperfections. So this collision of the moving electrons, conduction electrons, with the lattice phonon is dominant only at room temperature. At low temperature, a particular type of electron phonon scattering called enclave scattering becomes dominant. Uh, this small temperature scattering may be of 180 degrees scattering, whereas the normal scattering with phonon is small angled. So the collision with lattice phonon is dominant only at room temperature. At low temperature, this type of scattering is known as enclave scattering, and which is of 180 degree scattering. Now the second type is collisions with impurities and lattice imperfections present in the crystal system or metal system. And this type of scattering is dominant at very low temperature, approximately of liquid helium temperature. They disturb the period of the lattice. That is why the impurities or imperfections arises. These two types of collisions of conduction electrons are responsible for the electrical resistivity of metals. So these interactions of these moving electrons with these impurities or imperfections or lattice vibrations may cause the resistivity or resistance to the flow of conduction electron, and that's how the resistivity of metals arises. Let Royal be the resistivity caused by collisions with lattice phonons. L means lattice phonons, and rho I, that by collision with impurities or imperfections. I in the sense of impurities or imperfections. So Royal depends on temperature, and rho I is mostly independent of temperature. Rho is the usual symbol used for resistivity. I and L are suffixes, means that's due to imperfections and phonons. We could know that this resistivity due to interaction with the lattice phonons depends on temperature. As the temperature varies, its nature varies. So the Royal depends on temperature, and rho I is independent of temperature. It depends only on the amount of impurities or imperfections present in the metal system. So there is a rule connecting the resistivity due to imperfections and lattice phonon in the crystal. It is known as Matheson's rule. Uh, this rule says that it's the empirical observation that to a good approximation, Royal and rho I are independent of each other. So in brief, the rule says Royal and rho I are independent of each other. That is, the rate of the two types of collisions are independent of each other. Often Royal is independent of the number of impurities. That is, Royal is the resistivity due to interaction with phonons, which is independent of impurities. It is quite obvious. Also, uh, rho I is depends only on impurities and not on temperature. So rho I is independent of temperature. So both these quantities do not depend on each other. So that's what the rule says. Then the net resistivity of the metal can be written as rho is equal to rho L plus rho I. So this is that rule. It is the that is the resistivity due to the two factors, two types of collisions are independent of each other. Now another term connected with this resistivity is residual resistivity. So what is residual? You know what is a residue? uh, it is in that sense this term residual resistivity comes. It's a extrapolated resistivity at 0 Kelvin. This is caused entirely by collisions with the lattice imperfections because rho L is 0 as T tends to 0. That is, it is the resistivity resistivity experienced by the metal system at 0 Kelvin. So we know that rho L is dominant only at room temperature. So at 0 Kelvin this value is not significant. So this residual resistivity is entirely by collision with lattice imperfections. Okay. Therefore residual resistivity can be represented as rho I of 0. 0 the 0 inside the bracket means at 0 Kelvin. It's different for different specimens of the same metal because of the different concentrations of impurities and static imperfections in the two specimens. We could know that the residual resistivity is depends only on the imperfections. So um, even though it depends on the imperfections, it varies from specimen to specimen because the amount of imperfections or impurities present in the same type of specimen can vary. On the other hand, the lattice resistivity rho L of T can be represented as rho minus rho I of 0. So the resistivity due to the lattice interaction can be represented like this. The total resistivity minus the residual resistivity is the same for different specimens of the metal, even though rho I of 0 may itself vary widely. For many materials, rho I of 0 approximately 1 ohm centimeter per atoms present in the per atomic percent of impurity. That is for many metal system rho I of 0, that is residual resistivity, is approximately 1 ohm centimeter per atomic percent of impurity. Now another term connected with this resistivity is resistivity ratio. Resistivity ratio of a specimen can be defined as the ratio of resistivity at room temperature divided by residual resistivity. So it's a convenient approximate indicator of sample purity. You know how the purer the specimen, the lower the residual resistivity, and hence the higher the resistivity ratio. So that is the residual resistivity depends only on the imperfections present in the crystal. It does not depends on the lattice imperfection. So if this is large, if the residual resistivity is large, means resistivity ratio is small. So if we are given with a specimen of resistivity ratio of small quantity or very low quantity, it means residual resistivity is high. That means the imperfections present in the crystal is large. So or otherwise, if the resistivity ratio is large, which means the residual resistivity is small, that means the imperfections present in the crystal is very small. So if we know the resistivity ratio of a specimen, we can understand the purity of the metal system. That's how the resistivity ratio is important. Now, um, impurity concentration in a copper specimen is about 20 parts per million. This is an example. So rho I of 0 is 1.7 into 10 to the power minus 3 micro ohm centimeter. So the resistivity ratio will become 1000. In exceptionally pure specimens, the resistivity ratio may be as high as 10 to the power 6. In some alloys, like magnesium, it is as low as 1.1. Okay, now we have to discuss the temperature dependence of resistivity. Only Royal depends on temperature, because it's already known from our previous discussion that the lattice interactions with the interaction of conduction electrons with the lattice will depend on the temperature. This is proportional to the rate at which a conduction electron collides with the thermal phonons. There is also a contribution from the collision with thermal electrons. The collision rate with the phonon is proportional to the concentration of thermal phonons. For temperature above the D by temperature, the phonon concentration is proportional to the temperature. So this collision of the conduction electrons with phonons is proportional to the concentration of the thermal phonons present in the metal system. So if the temperature is above the D by temperature, the phonon concentration is proportional to the temperature T. So we can express the resistivity as proportional to temperature for T greater than theta. D by you will learn what is D by temperature in your next module. I will explain it there. At very low temperatures, for normal electron phonon scattering, Royal is proportional to T to the power 5 by T to theta raised to 6, where but at very low temperature, such normal electron phonon scattering is dominated by combined effects of club scattering, impurity, imperfection scattering, and electron electric scattering. Okay, so this is all about electrical resistivity of metals.